Hi, I'm Traversal. I'm a PhD student in the Technion working with our spectrum, and I'm going to present a methodology to add the size operation to concurrent data structures. So the size of the data structure is a commonly used property. In Java, for example, all collections and maps must implement the size method. But obtaining the size while concurrent insertions and deletions run is not trivial. So existing solutions, both in the literature and in concurrent libraries, are either inefficient or incorrect. There is no solution which is both correct and efficient in the literature. Java, for example, in its concurrent libraries, returns an approximation of the size. And this approximation might even be negative, and for this, Java has a special if that checks if the result is negative, it returns 0 instead. So, yeah. So you can look at the source code if you want. So we present the first solution for concurrent size, which is both correct and efficient. And for a correctness criterion, we use linearizability, which we heard about before, but in general, it means that each operation needs to appear to take effect once between its invocation and response. And our solution applies to both sets and dictionaries. But let's start with the basics, why this is difficult at all to obtain a size operation in both correct and efficient way. So let's start with the first attempt to ignore concurrency and simply traverse the data structure and count the number of elements. And this is the approach actually taken by some of the classes, concurrent classes in Java. So to see this solution, let's look for example, at this set, which initially contains 1. I'm going to use characters from Winnie the Pooh simulated threads. So here we have Owl, and he wants to calculate the size. So he starts running and traversing the set. And now Pooh starts running, and he inserts 2 to the set. At this point, Owl might resume his traversal and move on to 2. And now let's say that Tigger removes 1. Now this series of events might happen again and again in a similar manner. So Pooh might insert 3, then Owl might resume his traversal and continue to 3, and then Tigger will remove the previous element, and so on and so on. And so far, Owl counted 3 elements, right? And if we continue like this, it may count more and more elements, while the actual size of the set was fluctuating between 1 and 2 the whole time. So this is obviously not a correct way to obtain the size. All right, so let's try something else. For actually obtaining the correct size, let's take a consistent snapshot of the set and count the number of elements in this snapshot. Now there exist solutions in the literature for taking a consistent snapshot of a data structure, although there are concurrent update operations. So we can use one of the existing solutions and count the elements, and then we can obtain the correct size. But the problem here is that these solutions are not efficient, because each time the size operation will be called, it will need to traverse all the elements in the set and count them. So we want to do something better than this, and not traverse all of the set. So for that, what we need is to hold some metadata that we can compute the size based on this smaller metadata. And then we don't need to traverse the whole set. And this is an approach taken by some other classes in Java. All right, and now what's the simplest metadata you might think of? So it would be simply a size field. And from this, we can obtain the size very efficiently. Let's just read the size field and we have the size. But what about correctness in this case? So to maintain the size in line with the number of elements actually in the set, we need the insert and delete operations to maintain the metadata. So each time an insertion or deletion runs, it first modifies the set, and then it needs to also update the metadata. Now, the problem we have here is that, for example, let's say Tigger runs a deletion of 1, so we deleted 1 from the set, and now it's about to update the metadata. But before it gets to update the metadata, we're left with an inconsistent state, because the number of elements in the set and the size field are not the same, right? So if Pooh, for example, starts running right now, and he can observe that there are 2 elements in the set, but the size field still has the value of 3. And this inconsistency goes even further. So for example, let's look at this empty set. And now poo starts running an insertion of 1. And at this point, it gets preempted before it updates the size field. And now Tigger starts running a deletion of 1 and update the metadata by decrementing the size. So here in this case, you see how we can, like Java, have a negative size as a result. And we could, like I said, that Java does, we could return 0 in this case. But the point I wanted to convey here is that the size field is very unreliable, and it can contain bigger or smaller values than the actual size. And we want to have our size correct. So the problem we need to solve here is that the set modification and the update of the metadata are not done atomically. And this causes the inconsistent size, which can cause bugs and risk the reliability of our programs. So to solve it, we need to do the two updates atomically, and this way maintain consistency. And this is what we do in our solution. So in our solution, we hold metadata in order to be able to compute the size efficiently without traversing the whole set. And we also maintain correctness by modifying the set and updating the metadata atomically. And the way we do it is by having the insert and delete operations. We delay the linearization point to the metadata update. What I mean by this is that the insert and delete are considered as applied to the set, not when they modify the set, but rather only later when they update the metadata. For example, if you look at this set, and let's say now poo inserts 4 to the set, and he needs to update the metadata. But before he does that, Tigger might start running a deletion of 4. Now, at this point, the insertion by poo is not yet reflected in the metadata. So it means that the insertion is not yet considered applied to the set. So Tigger cannot simply delete 4 because you cannot delete an item that is not yet been inserted. Right? So what Tigger needs to do, we don't want it to just sit and wait and block until poo updates the metadata. We want Tigger to make progress. So what he can do is help poo update the metadata on behalf of poo, and then he can resume his operation. So this is what we do in general. We have operations, help operations that they depend on to update the metadata. Operations they depend on, by that I mean operations on the same key in case of sets. So this is the basic idea of our methodology, and let's delve into some more details now, starting with how we transformed a data structure to use our size mechanism, and then I'll talk about the inner workings of our size mechanism. So starting with the transformation, I'll demonstrate that on an insert operation. So an insert operation of a set would typically look something like this. Let's first search for the place to insert the key k. If you found k in the set, then you need to return failure, because a set is a collection of distinct items. But else you can allocate a node with k and insert it to the set and return success. All right, now how do we transform it to use our size mechanism? So first, as I said earlier, after we modify the set, we need to update the metadata. So here, after we insert a node into the set, we need to update the metadata to reflect the insertion. Another thing I talked about is how operations have to help operations that operate on the same key. So here, you can see it in this case, where if we find k, and k was inserted by some insert operation that is still running, that has not yet updated the metadata, then we need to help it update the metadata before we can resume our operation and return failure. And lastly, successful insertions and deletions need to inform helpers how to update the metadata on their behalf. And they do it by publishing some information in the node on which they operate. So for example, what insert does when it allocates a node is placing some information about this insert so that helper threads can know how to update the metadata on behalf of this insert. All right, now something we need to take care of here is the following. Because we enable help, then multiple threads might run concurrently and try to update the metadata on behalf of the same operation. And in this case, we need to make sure that the metadata actually gets updated on behalf of this operation, and that it gets updated only once and not more than this. So how do we make that how do we make sure that this happens? We do it by using suitable metadata that enables threads to determine whether the metadata already reflects a certain operation and update it if not. So this brings me to my next point, which is how our metadata looks like. This is our metadata. It's an array with 2 cells per thread, an insertion counter and a deletion counter. So this 3, for example, means that Pooh has so far successfully inserted 3 items to the set. All right, so how is this going to help us? Let's look at an example. Let's say that Pooh wants to insert 9 to the set. So what he needs to do is create a node and, as I said earlier, publish information about his insert in this node. So the information includes his thread ID and the fact that it's his 4th insert. Now Pooh is going to link this node to the set, and after he modifies the set, he needs to update the metadata. But it might get delayed at this point, and Tigger might start running a deletion of 9. So Tigger is going to encounter the information that Pooh left, and he'll try to help Pooh update the metadata. Now, the key point in using this form of metadata is that it's going to be very easy for Tigger to determine whether the insertion by Pooh is already reflected in the metadata or not. All Tigger needs to do is access the insertion counter of Pooh and check its value. If the value is smaller than 4, it means that the insertion is not yet reflected in the metadata. And if it's 4 or more, it means that the insertion is already reflected in the metadata and Tigger can simply resume his deletion. All right, so this is like the key point of using this metadata and not simply a size field is that this enables threads to easily determine whether a certain operation is already reflected in the metadata or not. Because all they need to do is to access the counter of the relevant kind of operation in the relevant thread and check whether its value is smaller than the required value. All right, so now what Tigger needs to do in this case is, because the value of the counter was 3, so it means that the insertion by Pooh was not reflected in the metadata. So Tigger actually needs to help Pooh, and for this he performs a cast operation and changes the value from 3 to 4. And if the cast fails, then there is no need to repeat it, because it could fail only if someone else has already performed it successfully. So this is our metadata and how we update it. Now, the whole point of this metadata was to compute the size, right? So let's see how we do that. So to compute the size from this array, what we need to do is to sum all insertion counters and subtract all deletion counters. This will give us the number of elements currently in the set. All right, so are we done here? Let's look at an example to answer this question. So let's say that we start with a set that no insertions or deletions were performed on so far, and out runs a size operation, starts reading the counters and computing the size. Now, when it reaches this counter, let's say that Pooh starts running and he inserts 9 into the set and updates his insertion counter accordingly. And then Kanga starts running a deletion of 9, deletes 9 from the set, and updates her deletion counter. Then at this point, if Owl resumes his traversal and keeps reading the counters in the array, it will see the modification by Kanga, but it will miss the update of Pooh. And this way it's going to obtain a negative size. All right, so we're not really done, because having a simple traversal is not going to work here, because we might obtain a collection of values that never coexisted in the array. What we need to do instead is to take a snapshot of this metadata array, and then compute the size in this form from the snapshot of values. There has been a lot of work in the concurrency community on consistent snapshots, and people designed algorithms to kind of magically obtain a consistent snapshot of data structures. Now, it would be too complex to get into the details here, but we draw ideas from these works and use them to produce our snapshot mechanism for the metadata array. And note that I did talk about snapshots at the beginning of my talk, but this is not the same as I'm talking about here. Because in the beginning, what we said was that we could naively take a snapshot of the whole set and then count the number of elements in this snapshot. But this is a snapshot of, like, before I talked about a snapshot of the whole set, and the set could contain millions or billions of elements. What we do here is different because we take a snapshot only of the metadata array, and this contains only 2 cells per thread. Usually there are tens of threads. So we take a snapshot of a much smaller piece of data, and so it's much cheaper. All right, so this was our metadata and the way we update it and use it to compute the size. So let's recap the basics of our methodology. So we modify the set and update the metadata atomically. For that, we need dependent operations to help update the metadata. We designed the metadata in a way that enables them to count each operation exactly once. And we use the metadata to compute the size by taking a snapshot of the metadata array, which is much smaller than the whole set. And for taking a snapshot, we extend previous solutions for snapshots. And as I said, I didn't really get into these details, but all details of our snapshot mechanism appeared in the paper, as well as the full transformation, because I covered only the insert operation, but we also say how to transform the list and contains. I also didn't talk at all about the fact that multiple size operations can run concurrently, and that introduces some additional complexity. So we handle this situation also in our paper, and we also bring proofs to the properties of our methodology, to linearizability, to the progress guarantees, and the time complexities. Moving on to the evaluation, we implemented our methodology in Java. The implementation is available online on GitHub, and we ran the experiments on a multiple Linux machine. Now, we ran our experiments on 3 data structures that we transformed to use our size mechanism: a hash table, a binary search tree, and a skip list. And we also ran the experiments on snapshot-based implementations taken from the literature in order to compare the throughput of them with ours. And here I'm referring to implementations that are based on taking a snapshot of the whole set. All right, so the first measurement I'd like to show is this one, in which we altered the size of the data structure, and we wanted to check how this affects the performance of the size method. So we initially inserted this number of elements to the data structure, and then we let 32 threads run concurrently for 5 seconds. 31 threads ran insertions, deletions, and contains in this distribution, and 1 thread repeatedly called the size operation. And we counted how many times it performed it executed size per second. So the throughput of this size thread is what you can see in the graphs. So on the left, you can see that our methodology is actually insensitive to set size because the throughput is roughly the same for different set sizes. And what you can also see is that our methodology outperforms the snapshot-based implementations. Actually, it outperforms them by orders of magnitude, and this is why the scale of the 2 graphs is different. All right, and another thing I wanted to show is how our size methodology scales. So for this, we didn't run just 1 size thread, but rather change the number of size threads between 1 and 16, but we still let other threads, 32 threads, run insertions, deletions, and contains operations. And what we measured here is how many size operations, all of these threads, of the size threads performed per second. All right, so this is the total throughput of all the size threads. And you can see that the throughput improves as we have more size threads. So this demonstrates the scalability of our approach. And you can also see again that our approach performs much better than the snapshot-based approach. In the paper, we also measure the overhead on the original set operations, insert, delete, and contains. And we showed that in order to obtain the size in a both efficient and correct way, we do have to pay some cost, which is the fact that the insert, delete, and contains need to maintain the metadata. And for this, they lose up to 20% of their throughput. But on the theoretical side, we do preserve the progress guarantees of these methods, which means that if the original methods were lock-free in the original implementation, then in our transformed implementation, they remain lock-free. If they were weight-free, they remain weight-free. And the time complexity of these methods is also preserved. So to summarize, we developed the first methodology for adding a size operation to sets and dictionaries, which is both correct and efficient. And our evaluation shows that it's by orders of magnitude better than existing solutions, and that it's also insensitive to set size and scalable. Thank you.
Nice talk. So my first question is like in your material you had two separate columns, right? For insert and delete, the number of insert and delete. So I was thinking like on a perfect basis we only having one at a time, right? So do you think of like combining or is there any problem of having just one column instead of two?
Do you have one?
Oh sorry. So in your material
just get back to the
sure.
Correct, whatever is there in this kind.
Yeah. So there are two columns, right? One is insert and one is delete. So I was wondering, do we need two columns or can we do that in a single column? Because each of them is only each row represents one thread, right? So only one of the two will happen at a time.
Each row
is one thread, if I'm not wrong. So
I mean, each row represents a counter of a single thread, but multiple threads can update this field because other threads might help this thread update. But I mean, it's true that I didn't I didn't explain all the reasons that brought us to use this order, right? Not just one side field, but you're right that okay, if we wanted to have just a single field per thread, like only the number of insertions minus deletions, like the number of elements it currently has in the then the problem there is that, for example, if there is if this thread performs an insert and then a delete, right, and then somebody wants to help him update this insert, for example, right? So he needs to know whether the insert has already been updated or not. And like, let's say we start with 0 as an example, and then after the insertion becomes 1, and after the deletion it goes back to 0. Right, so if someone comes to help, he doesn't know when he sees 0, it's already reflected or not. But this is actually solved if you can add a sequential number like right next to it, and then it could be solved this way. But we just use this, which is simpler than having two values always updated using us together.
One last question. So in your data set, in the evaluation, there was 95% of contains population. Right?
Yeah.
So does that actually modify the data?
That's what.
Does that actually modify the counts in any way?
I mean, we have so we have the 95 contains, which do not modify metadata, but the 2% and 3% deletions and insertions are the ones that modify metadata. And in fact, in the paper, we also have, this is like a read workflow, but in the paper, we also have update intensive workflows with 50% content and 30% and 20% insertion conditions, and we show how they affect performance. But the effect is similar. It's true that with the more updates you have, the throughput gets a bit less good for size, but still it shows the same trend.
Thank you.
So your work seems to be very time efficient to create this work. How did you think how to navigate tracking metadata actually adds in terms of space requirements?
How the space requirements?
Yeah, so doing obviously adds a little bit of gain, but not true, not really.
Yeah, so we didn't check that effect of the
So when people are doing performance studies on these sorts of data structures, they vary the proportions of the various operations that are being performed. And I think you just talked about varying the performance that the insert, delete, and contains. But if you're evaluating this, surely you also need to look at the frequency with which size is actually evaluated relative to the other operations.
And what we did is, in our experiments, we just ran.
Yeah, I understand that, and I'm suggesting that that is not actually giving you a very accurate picture. If size is actually computed very rarely, then you're going to be far better to stick to the original implementation where you traverse and maybe even lock the whole data structure what you're doing, if it is done very infrequently.
Yeah.
If it is done very frequently, then yes, you need to do this kind of thing. But I think you need to look at the frequency of the size operation relative to the other operations to really get an accurate picture of the efficiency of your solution.
Yeah.
I would also think it would be a useful thing to look at some real applications that use these kinds of data structures to see how the frequency with which size operations are actually called in practice in real applications. Because I think that would be a useful thing to look at in deciding whether these solutions are actually giving you a real gain in practice or not.
Yeah. So I agree that this, of course, matters, and if you just take a size operation, run a size operation very, very rarely, then you don't want to put this overhead on the other operation.
And after all, this is a decision we've been making for decades with sequential programs. When we have container data structures, we make a decision as to whether size is going to be computed by traversing the data structure when it is called, or by computing it incrementally and and opposing the cost over all the calls. We make that decision. We know that's a choice.
Yeah, actually, like as I said in the beginning, like even in Java, there are some classes which implemented by Traversal, and some classes that hold metadata, which is not exactly consistent, but they do hold some metadata. So you're right, they take different approaches, but yeah, for example, like in the graph that I showed, then like the all right, so yeah, it's not really easy to see, but for example, this solution here in light blue performed only with the traversal performed only one size operation per second, or even less. So we performed much worse. And the other snapshot-based solution performed better, but it has a very high space usage. So I'm just saying, like, it's probably still, even if we perform the size a bit more rarely, our solution is still much better. You need to perform the size very rarely in order to actually use our solution. But yeah, we didn't check that.
Right, that's a choice. It's a choice that the clients can make.
Yeah. Okay.
First of all, excellent talk. Great to hear. One question. So you're assuming sequential consistency here, I assume?
So we designed it for Java. So we use Java memory.
Right. I guess I was wondering if you had thought at all about weak memory, how that would affect the design of the structure, or if you could make it more efficient.
So actually, most of our modifications are done using a class operation. So many guys did our localization points, and there are just really a few write operations which we do in the holiday semantics of Java. And
I think I was thinking more in the size operations, in the reading the size. Maybe you didn't get so much detail about
yeah.
if you're just doing a bunch of readings, if those would be stale reads,
Yeah, so I mean, we just did it for this in Traversal.
So if a client has like a long-running application, there might be like a lot of insertions and deletions. And one thing with keeping track of the number of use this, you might run into any integer overflow issues that you wouldn't if you were just hashing the size directly. Do you address that at all, or do you have mechanisms for improving the metadata table?
You're asking about the overflow for our countries.
Yes.
Yeah, so actually we didn't, I mean, I think that even if many operations are going to take effect, it's going to take a long time before anything overflows there. And I think actually, I don't know, I think that also maybe even in Java they don't really handle it specifically, but I need to check that, but we didn't take care of any overflow issues. I just think it's going to not happen during the lifetime of the program.
One last question.
Thank you for the interesting talk. Maybe an eighth question, but very early you presented a solution with just the size. And you said the problem was that you're updating the set and then updating the size and it's not atomic. Did you compare it to the approach of just making that atomic?
No, so I think it's fairly incomparable because these approaches are incorrect. So they can obviously perform much faster than us, but it's just they don't give you the correct size.
No, they don't give you the correct size because the two operations are not
Correct.
But maybe.
You're asking whether we compare to just a solution using blocks.
Yes.
Oh, all right. I see. So actually, we have another student in the group who works on trying to have a size solution using blocks, and just using a very naive approach you talked about. So she implemented it, and it's performing very poorly as expected, but she tries to come up with better solutions using more delicate blocks.
Okay.
Thanks.
Thanks.